Hello, I think we're live now. As usual, I'm gonna run some checks, make sure that you guys can kind of hear me at least, and that the sound isn't too loud. In fact, am I live? Yeah, seems to be live. Wait, what? Remove extension? Why is McAfee installing shit? Why do I even have McAfee? What the hell? Let me just like remove everything, because I didn't realize I had so many programs open at once. I didn't realize I had so many. Yeah, so we are delayed a little bit, definitely. But I think that's all the programs now. Okay, good. Yeah, I have no idea why McAfee is still installed on my computer, because I'm sure I uninstalled that stuff ages ago, but as you all know, McAfee is like, it's like a plague. It's different, it's very difficult to get rid of it, isn't it? Hello, Antonio. Bom dia. Boa noite. It's a good night here in the UK. I guess it's boa tarde there in Brazil, isn't it? Good to see you, my man. Yeah, as you can probably tell from the title of the stream, we're actually going to be doing some C++ today. We've not done quite some C++ in a while. So yeah, let's get started with it. First of all, let me show you guys what I would like to get done today as a kind of MVP. So we had the 6502 emulator online last time, right? Sadly, I may have to leave midway though through, but I like this topic. Yeah, thank you. Yeah, no worries. I mean, if you're busy, nothing we can do, right? So I think it was called Easy 65K. There you go, that's the one. And if I open my notes here, I should have some sort of, there you go, program that kind of works. So okay. And this is the program that we wrote last time. I mean, actually, in the last stream, we only wrote enough of the assembly to do a quarter of the screen, right? Because there was some issues with memory wrapping around. But then on last weekend, or this weekend, I actually read a little bit more about 6502, and I figured out how to kind of do this extra level of indirection. So you can essentially work with pointers that aren't just bound to 256 values for offset, which basically means you just load a word, right? Which is like 2 bytes. But you know, this is the program that I ended up with. So essentially, I want to be able to run this program on my emulator, right? And it's not too difficult. It's not too difficult at all, because once you assemble it, if you click on hex dump, you can kind of see what the instructions are. Yeah. So for example, the LDA seems to be FF, right? FF01, or maybe not. Oh no, this is incorrect. Yeah, I am now kind of disassemble. Kind of wondering how we can get a binary here as a test binary so we can test it. Well, for sure we can just use the other emulator, right, that we had. 6502. It was by Masaryk. This one here. So if we paste the source code here, and we simply, is this supposed to be the source code? Paste hex source code or drag drop. Emulator, no. We wanna, I'm looking for an assembler, not an emulator. So the actual compiler for it. There you go. So that's a little bit better. If we assemble it, you can see what the source code is like, and we can download the binary here. So I'm kind of gonna just like work from this basically. We're gonna write a few simple assembly programs, and then we're gonna try and run them from C++, right? So I'll show you guys how we're gonna lay the project out in a second. It should be very simple. It's this emulator should just be a switch case, a big switch case containing all the possible bytes for the operators and then what to do inside the switch case. But let's generate this one, right? So let me see if I can kind of put this somewhere useful. So this is the pixel drawing program. I'm putting on the other screen here. Just give me a second. Close. Now what can we do? Like, let's make this even simpler now. So just the program to load as a value into the accumulator. So if we kind of assemble now, you can see that it becomes a lot simpler, right? So we're also going to download this binary here, and this is just LDA and storing it to B1. So, right. Let's generate a binary, download it. Okay, so I think we can work from these two things, right? So maybe it'll be ideal if we can kind of start this program here. I'll be very happy if by the end of the stream we can do something with this binary. So in other words, this is actually doing something very simple. It's loading the value 01 here into the accumulator, and this is the opcode for it. So every operation in assembly will be converted to a machine operation, a machine number, right? So a binary number. And in this case, it's a hexadecimal. But yeah, this LDA function here, it's converted to A9. And this means that we're loading into the accumulator the literal value 01, not a memory value, a literal value 01. That's the first instruction we're going to try and support. And then, as you can probably guess, we have SDA here, which stores the value that's currently in the accumulator to memory value B1. And that opcode is 85. 85 means that we're going to store whatever is in the accumulator into the memory B1, right? And memory is just like if you think of it as RAM, that's basically what it is. It's a very, very small RAM for the 6502. In fact, maybe we can actually look at what something looks like. So, hello Robin, hello, good to see you, man. So let's look at the architecture of the NES, right? So the NES, why did it just delete everything that I wrote? So the architecture of the NES is actually fairly simple. And I chose the NES here because, as you can probably guess, it uses a 6502 base processor, right? Or it used, because they don't really do these anymore. But maybe, can we get a diagram here real quick? Can we get a diagram here real quick? So the NES uses the Rico 2803 CPU, which implements the instruction set for 6502. As well as some other hardware on the side. I'm trying to get the actual, like, the complete kind of architecture for it. There you go. So I guess the APU is the main CPU, and then the PPU is like another CPU for just for picture stuff, just for doing the sprites and like drawing it to the TV, right? So that's what we essentially do here. In this video, we're only gonna do the CPU itself. We're only gonna emulate programs that can run on the CPU. So when you look at NES emulators online, what those programs actually do is like they have a 6502 emulator, and they also emulate all the other pieces of the puzzle here as well. So they have software emulation for the PPU. They have, obviously, you know, bootstrapping code for the programs, for the games, the BIOS stuff. They have like abstractions on the RAM and everything like that. Do you intend to eventually make a full NES emulator? I don't know. Let's see. I mean, it depends on how difficult it is, really. Because if it's too difficult and it requires me to do a lot of research and kind of leave the other projects that I have currently on the channel out, then maybe not. But the NES is known to be a very simple system to emulate, though. Very, very, very easy. I'm still not sponsored by Coca-Cola, but I wish I was. But yeah, today we're gonna just be doing the CPU, right? So let's get started with it. And then once we do, we can probably take a look back at the CPU itself, and we're gonna take a look at what flags are available to us by, from the 6502 processors, what registers we have to emulate and whatnot. So let's make a dir 6502, 65K. I don't know what to call this project, to be honest, so I'm just calling it anything. So yeah, in here we can just, I guess, touch the cmake lists.txt. Maybe we should actually do a... Maybe we should do a kind of a C++23 project and actually try to use modern C++ on this. That'll be cool, I guess, right? Well, in that case, I'm going to just copy whatever content file I have for a different project in here. And I'm also going to copy the cmake presets. Okay. And now we can kind of just go from there, right? We have everything we need, basically. Obviously, the content file is going to be a little bit simple because I kind of feel like we only have... We only need to use FMT, right? FMT will be the best one. So yeah, let's see what FMT version we can get here. FMT, C++. So we are on version 10. Okay, copy to clipboard. I'm gonna paste it here. Yeah, we can do a G test as well, right? Why not? Let's put a test binary here. So, right. So what do we want to do here? Maybe we do test-driven design actually and start writing the test first for what, because that actually ties quite well with what we need to implement. Because, quite honestly, guys, what we're going to be doing is we're going to be looking at the instruction set quite a lot. So this is the instruction set for the 6502. And for example, we know for a fact that LDA, right? LDA was one of them, one of the instructions we wanted to support. So LDA absolute value here. So this is, does it show the opcode? Yeah, A9. So immediate mode A9, we know what we should be reading from the binary file, from the ROM itself. And then how many instructions, how many bytes it takes overall. So that includes the opcode and then the bytes. And then the cycles is also worth knowing because we're going to have to implement timing eventually. So it runs at the same time as a real 6502 processor would do. But yeah, this is what we're going to be doing. So we're going to be looking at this and then just putting it into the code. For now, I think we're just going to make a folder here and call the 65 or the emulator. $65K emulator. Actually, let's just rename it to emulator. CMake. Yeah, now I feel like home. Yeah. It's been a while actually for me. I've not done any CMake at work in maybe like 2 weeks now. But I'm doing some CI work now, which means I get to rewrite a lot of CMake to make it more efficient. So I'm going back to CMake again. But soon I'll be back on Rust. So yeah, we're going to be putting everything into here. So let's just create another one here. Let's add an executable. Let's call it the emulator. And let's just put a main.cpp there, shall we? Now, I want to be able to use modules. But in this particular... Yeah, let's build it as a library, as a module, right? So add library. We've got that. And I need to look at the kit where modules... C++ modules thing again, because I keep forgetting what we actually need, The experiment is over is the one we're looking at, this one here. So, for CMake, as a library, what we do want to do is just add a library and then target sources instead. So target library, emulator. Yeah, because we need to activate the C++ modules. In fact, right, I mean, Yeah, we could write all of this, but I already have this written somewhere, to be honest. There you go. What's on this one? Let's see if we can reuse some of this shit. I think this is a stream that we did previously where we did some of the modules work before. So no, this is not. I know one that has. So if we look at, sorry guys, just bear with me for like a minute until I set everything up. There you go. This one will have modules, and it's actually my base64 implementation. Like a fun fact, I keep getting like people coming up on GitHub for this particular project and asking me to improve the performance of the base64 stuff. Like every maybe 2 or 3 months I get someone asking that, and it's becoming annoying now. I'm gonna have to do it at some point. But anyway, so there you go. So this is kind of what I want. Target include directories, target include directories. Yeah, we're just gonna copy and paste some of this, the stuff that we need anyway. Oh. This doesn't happen to be a copyrighted song, right? Hopefully not. Anyway. Yeah, instead of that, we're gonna go for Emulator. I mean, it's essentially what we had before. Cool, but I also need some stuff in the main CMake files, right? In the main CMake files, where is it? It is here. And yeah, so we need all of this into my main CMake file, CMake lists. I think I need 328, I believe, for modules. I'm not entirely sure. Which version do I have? Yeah, 328. And then we have the project name, which would be, I guess, 65k Emulator. And languages, just the XX for our case. Let's put 23. C++ 23 is good. Okay, I think that's everything that we need to actually have for all of this to work. With modules. I've got the CMake presets already, so that should be set. Yeah, good. Now, let's actually just rename this to something like Emulator itself. And then we can add subdirectory here, which will be the emulator, right? I think I need to reload the window, actually. So CMake triggers, CMake is triggered on this. Right, there you go. So now, I think I want a Ninja Clang build. All right, so what is the error? CMake CSS compiler is not a full path to an existing compiler tool. Yeah, that's not the compiler. Wait, what? Clang++ version. I've got Clang 14, not 17. Oh. Do I have 17? Yeah, I do. So what is it complaining about? So Clang 17 is the issue here. I just don't understand how he got the wrong compiler here, or the so this compiler. CMake lists error trees. What am I missing in my project? What am I missing in my project? Language is CXX. Yeah, I mean that sounds fine. Project. Like, what the hell is it getting this bath from for the compiler? I mean, that's interesting. Can the project name start with numbers? Yeah, that's a good point actually. It's not gonna be that, right? If it's that, dude, I'm gonna laugh a little bit. Nah, yeah, still the same issue. Does the project name need to match the folder name? No, it doesn't. It can be anything you want in CMake. Yeah, I mean, the only interesting thing is that we are basically passing the compiler here. Scan dependencies. We need all these flags anyway for modules, but somehow Clang++ 17 is coming from like this. Like how is that right? How is that right? I don't have anything in my settings, Jason, right? Ah, could it be this? Could it be this by any chance? There you go. Right, funny story. Funny thing. We had the toolchain file from the NDS stuff, and that somehow was making things a little bit worse. I don't know what exactly it was doing, but you know, this seems to fix it now, so we're good. I'm trying to finish my Coke very quickly. So yeah, if we do module, is it module, and then we have. I can't even remember how to write the modules, you know. So let me look at the documentation again, because I keep forgetting a module, and then we have all the includes. Yeah, I was just wondering like where to put the includes. It has to be between the module and the export module. 65K. Oh yeah. And then we have all the functions here. So export. Now we need the 65K. And this is where we're going to put all this stuff, right? So for example, we need the registers here. And that would be A, X, Y, and the stack pointer, and the PC counter here. All of that is going to have to go in here somewhere. And we can probably just have variables, right? And they each are, I believe that they're each a use UH here, right? So I am getting messages. Where am I getting messages? Nowhere. Not important. And then we're also gonna have obviously the memory. So you're gonna have like the 0 page, which is like the first, I think is like FF bytes. And we're gonna have the main memory. And maybe we're gonna have some video memory as well, some VRAM, right? Now, video memory isn't really part of the 6502, as you can probably guess. However, we do need something to represent graphics here. So maybe we can paint this using like SDL or something like that. That would be quite cool. So we can allocate something like 32 by 32 bytes just for the memory for the video, right? In fact, I don't actually know the specification for 6502 memory itself. The MOS 6502 is an 8-bit processor that was designed by a small team led by Chuck Peddle for MOS technology. That is a very popular one. I've heard of this one before. Now, memory addresses width 16 bits, right? So it has 16 bits or 2 bytes. That's the word. So actually the calculator is going to be helpful for us here. So what it can do is it can do, if we select hexadecimal and do FF, this is how many addresses you can, in theory, address, right? So you can have a vector of 0 up to 65,535 bytes, or bytes of memory, right? So that's what we're gonna have to do. But in practice is not actually what you get. So for example, I'm not sure how much memory the NDS had available. Memory in the NES. Oh no, yeah, it was up to 64 kilobytes. So yeah, is this here. And included in that memory is the 2K byte of CPU RAM. So actually, you only have 2K accessible to you for the CPU RAM. Pause to access PPU, APU, WRAM. Yeah. So what this usually happens is, like, you know, when you have controller handling, for example, when you're pressing a button, that button is actually mapped to one of these bytes in memory, one of the 65K bytes. And the hardware that's like handling the interrupt or whatever it is for the button press would be watching that particular byte in memory to see when it changes. So I guess, you know, maybe you can only access 2K of RAM itself, but a large portion of the other stuff would also be for the PPU, with things that are going to be holding the pictures and the frames, APU, controllers, you know, everything else. Yeah, very cool. Actually, I think Robin is probably much better at this than me, because he seems to play around with hardware a lot more than myself, so. But usually that's how it works. So yeah, let's begin by doing the registers, right? So let's read about the registers and see if we can abstract all of it, because that's what we need to do. So we have this Rico. Let's actually base ourselves on the Rico one, which is the NES CPU. Specifications. Now, can we get the actual specification somewhere where it says, like, you know, these are the registers that you can access, you know, and everything else? Jesus, like, where is the actual technical specification? Oh, there you go, registers. So let's take a look at the registers. So these are the ones we have. We have A, X, Y for the indexes, program counter, PC, and stack pointer and status registers. P has 6 bits used for the ALU, but is byte-wise. Ah, I guess these are the flags, right? So these are the flags, so the status flags. Yeah, there you go. So, you know, as well as the registers, we also have the status flags, and you can see here what they kind of do. So certain instructions can set some of these flags. So for example, when you add 2 bytes together, it can overflow, right? So usually when it overflows, the carry bit would be set, and the overflow bit would be set as well, or something like that, to make sure that, you know that the value wrapped around or something. So yeah, it's very useful to have these, and you can see that this is 7-bit. Yeah, this is 8 bytes, and we're gonna have to have that on the, I guess, on the registers as well, right? So let's do that. So we have, let's do another export here. So export struct registers. And then we're gonna have std uint8t, and that will be A. A, X, Y, stack pointer, and there you go. So we have AX, and then we have Y, and we have the stack pointer or the PC counter, and then the stack pointer here, right? And of course, we're gonna have to include C student. In this case, I believe that's what it is. So that will contain all these types, or maybe not. Okay. uint8t. So what is this CST def by any chance? Oh yeah, that should contain everything. Why can I not find? There you go, uint 8. Wait, what? C++ 13? What is this? Why is it not available? What am I missing here? Jesus. Which header includes all this stuff? C stud int. It'll come from somewhere, surely. I'm confused now. Like, why am I not able to use this? Why am I not able to use this? cstdint, that's the one, yeah. And it contains uint at. Maybe it's just an issue with the IntelliSense. No type name that. uint at. Right? What am I doing wrong here? I'm so confused now. I am so confused right now. Have I made a typo? Have I made a typo? No, I have not made a typo, right? What's in std now? Oh, there you go. Now it's available. I don't understand what happened, because we did have that same header before. Making me doubt myself. There you go. Now it's appearing. I think it was just an IntelliSense fluke. Yeah, so these are the registers that we need. Right. There you go. It was just a fluke of IntelliSense. So we basically have the registers here. So we have registers, and then we also have, I guess, a byte here. Actually, the flags have to kind of be a bit field or something like that, right? So what is the C++23 bit field or something? It's not bit field. There's a new version of the bit field in the standard. I think it's called bit something. Is it bit depth by any? No, it can't be. Three-bit unsigned in field. A lot of values are 0 to 7. The reason why I'm gonna be doing them as bit fields is so we can access a particular byte in the field, right? Because that's what the flags are. You have to be able to access the, for example, the decimal flag, or the interrupt disable, or whatever it is. So yeah. But I don't want to use a bit field because I know there is like a better alternative today. What is it? C++ a bit field versus bit set. That's the one, right? That's the one. I want to store bits in an array so I can either do one of the following two. So struct bit int data is 1. And this is the one here. So let's look at stud bit set. Are you guys too young to know Donkey Kong? The sick game. That's why I'm gonna skip it, because I'm gonna get copyright striked by Nintendo. But yeah, Donkey Kong Country was one of the best games for the Super Nintendo. So how do we use this? So the class template bitset represents a fixed size sequence of n bits. Bitsets can be manipulated by standard logic operators and converted to and from strings and integers. For the purpose of the string representation and of name directions for shift operations, the sequence is thought of as having its lowest index element at the right in the binary representation of integers. Bitset meets the requirements of copy constructible. Okay. All member functions of std bitsets are const expert. It's possible to create and use bitset objects in the evaluation of a constant expression, which is good. That's what we want. Right, let's look at the examples and see if we can quickly whip this out. So const expert for bitset for. Okay, right. So this is the value 10. And how do I get like one particular bit? Oh, that's cool. So you can do like strings to it. That's kind of also const expert. That's cool. So we can compare the whole value, or can we get like a particular position? So set a position equals 1 flip. We must be able to get them, right, as well. If there is a set, there's a get. Now, the thing is bitset actually implemented here? Yes, it is. Bitset, there you go. So we want 8 bits, I believe. Right? Is that how we use it? Size n. And the number of bits to allocate storage for. Yeah, so we have 8 bits. And this will be our flags, right? And again, this is like, we're gonna just copy and paste it from the website because I don't want to have to do too much here. So these are our flags. One of them is always on. So 2 of them have no effect. So see the B flag, no CPU effect, always pushed as 1. That's cool. But anyway, yeah, cool. We got all of that now. So we're basically slowly modeling the CPU. That's what we're doing here. And it's actually very easy. So memory, now the memory is interesting because we want to have, as I said, this many bytes available to us, right? So essentially what we're gonna do is, I guess we're always gonna have an array here of size ff, and it's going to be a uint t array, as I said, as ox ff. That's the size of it, right? And it's going to be 0 initialized, correct or not? Expected an identifier. You're damn right. And then we have the memory here. Let's initialize everything to 0, shall we? Just in case. I believe that's how you 0 initialize everything. And yeah, so just by using 2 little structs here, we've been able to model the CPU pretty well. So you can think of the 6502 CPU as just a simple state transition now. So every time you read a byte, you're going to do some operation and you're going to change these registers internally. You're going to change some of the flags and return a new representation of the CPU, right? That's all we're going to do here. So let's go. Clean build. Powerline, yo, are you hacking the FBI? No, I'm not hacking the mate, I'm just doing an emulator here. Nothing too difficult actually. But yeah, welcome to the stream, Powerline. And by the way, guys, drop a like on the video. I hope YouTube shows it to more people. But it only does that if you guys drop a like on the video. So, and yeah, stay tuned. So right, first things first, right? So what are we gonna do? Let's move those files that I downloaded. You're part of Anonymous. I am, yeah. Part of Anonymous. That's why that's why you know my name and basically where I live as well. You got the same beard as the mask. Thank you. That's what I'm aspiring for, really. That means I need to shave, right? I need to shave tomorrow. But thank you. So let's move those binary files that are kind of ROMs for the 6502 into here, right? So that's what I'm gonna do. MTC users. I think I called it LDA or something. And the other one was pixel draw it into here as well. Right, so we've got two binary files. Open anyway. Can we have a binaries viewer? There you go. So the first thing we're going to try and emulate is this one here. So LDA. Oh, why is it not start? Why is it not reading it? Binary viewer. Why is binary viewer not working? That's not what I want. Maybe if I reload the thing now. The song you're playing is pretty scary. Yeah, it is pretty scary. Do you know why it's really scary? Because I get a copyright strike every time it plays. So thank you for reminding me. And I've skipped it now. Yeah, that binary viewer doesn't do shit. So let's move it. Let's move it out of my installation here. Uninstall binary viewer. Yeah, why none of these binary views actually working? Yeah, we can just do a hex dump, right? It's not a problem. So hex dump, and then we have LDA store, and this is what we kind of have. And this is showing me, oh yeah, hex dump is kind of shit. So how do I convert this to little endian? Sorry, hex dump. Hex dump minus C, that's the one. Yay, there we go. You know CMD? By CMD, do you mean the Windows command line language batch? No, I don't. I wish I knew more. Of course you do. You are, dude. That's a lot of spamming there. I'm not a hacker, by the way. Right, so the first instruction is A9, right? And we take in that. So what we're gonna have to do is like, we're just gonna have to basically have a function that will state transition, right? So transition. Yeah, a function that will take a CPU and it will take the memory of the instruction itself as well. And then it will execute that instruction, right? That's what we're gonna do. So yeah, what can we do now? So we have a function that will return CPU, transition, or execute command, right? Execute the command, and then what we're going to pass in here is a uint.at which is the actual command itself. I'm going to put a 2 here, you're going to see why. And then we have the operand here. And we're going to have the operand there. So there are different types of commands for the 6502 assembly. For example, we had A9 here, which is loading into the accumulator the number 01. And then we also had the store into the memory B1, whatever's in the accumulator, and that's 85 B1. But some functions, so some instructions actually take more than 2. So instead of it being just 2 bytes long, they are 3 bytes long, right? And you can see that in the instruction set. If you look at the instruction set, you can see that some of these are 3, for example. You know, bytes takes 3 bytes here, 3 bytes there. Bye bye, Powerline. See you later. Thank God he's gone. So yeah, we kind of need 2 functions, 2 different functions, right? So we need one for, it doesn't have to be 2 functions now, but we're going to implement the one that only does 2, right? So the operand, the command and the operand. What the fuck was that about? Yeah, I don't know. I should probably be able to ban people, right? I don't know how to ban. Oh, there you go. It's just as easy as like putting someone on timeout, I guess. Hide user on this channel. Does that work? Yeah, there you go. That works fairly well, doesn't it? Wait, I undid it, but I didn't mean to. Well, do you work with Anonymous? I wish I did, yeah. Because, you know, if you're working for Anonymous, you definitely say it out loud on stream to a random 12-year-old that just joined your stream. Yeah. I mean, some people online are just cringe, man. It's ridiculous. But, you know, Robin, since you do videos now, you should probably learn it. Just ignore these people, dude. The best thing you can do. Never stress over, like, online trolls, basically. And this isn't even that bad. I mean, bigger streamers have it worse. Bigger streamers have people actually doxing them and finding out where they live and saying it out loud to, like, millions and thousands of people. There you go. Sorry, man. I'm going to put you on timeout. Yeah, so we need to do that. Like, essentially what we're gonna have here is a big switch. Like, we're gonna have a switch on the command. And then you're gonna say, you know, if this is a 09, for example, A9, we're gonna do the load into load value into accumulator. So that's what we're gonna do here, and this is what an emulator is. We've done. This is the stream, by the way. Not really, but yeah. So yeah, I mean, let's look into how we can do this, and then if things didn't work out well, I guess we can include FMT here. Oh, FMT. But before we do that, we actually do need to kind of find the package, I guess, in here, right? I'm not sure if I've Conan enabled. I'm not entirely sure now. Let's check out though. So if we do Conan, install, output folder, release, let's do the debug build. Invalid setting 17 is not a valid since... Oh, what the hell? Oh yeah. That's probably because I have to do a pip. Probably because I have to do that. Okay, so we've upgraded our Conan, which means it should now take the Clang 17 compiler settings just fine, right? Except it doesn't. Successfully updated invalid settings. Not valid settings for compiler version value. Like, why? Why not? Why not? Ah, okay, this is GCC as well. So what we need to do is, I guess we need to just edit the default Conan profile, right? There you go. That's better. I'm not sure why it was like version 17 in there, but either way. There you go. That's better. Oh no. What is going on here? Missing package pre-built. You can try. So build. Oh, why is it missing the pre-built package for FMT if I'm just saying it to rebuild everything? Okay, that's even worse now. What is the issue here? CMake error. First of all, did it build with the right shit? We got Clang 17. This is the average C++ package manager experience right here for you guys. Replying to a text. Do you have it in your Conan TXT file? Yeah, I do. Well, it's just a FMTNG test here, so it should be fine. Just gonna check a message real quick. Okay, yeah, so let's see what the error is. Maybe we can figure it out. So C++ is not able to compile a simple program. Follows with the following outputs. Unrecognized command line option, C++, libstd, C++. Yeah, another issue on the Conan profile, I guess. That maybe works with GCC, I don't know. Profiles default. I mean, it seems to be fine here. Build type debug, whatever, version 17. Compiler version 17. Like, what the hell? What in the hell is it doing? Thing is, it's not really giving me a nice error either, so I'm just gonna have to kind of try and make sense out of this. Unrecognized. This is kind of bad. This is kind of bad. Clang should be able to recognize that. Yeah, I don't understand why it's like not compiling with Clang. Maybe it's like, maybe it's picking up the correct compiler from the profile, but it's still trying to pick up my my actual like normal profiler, my normal compiler. So let's see if we can just set it here. Clang ++17. Oh, this is CXX. CC. Clang ++ Clang 17, right? Ah, it works now. Yeah, that was why. So I thought Conan sets up the correct compilers, but clearly there's something going on there. Anyway, so we have things built now, and we have a Conan directory, which means that, do we also have Conan in here though? That's what I wonder. Unix shared, Conan debug. Is Conan release here? Yeah, I thought I didn't have one. I know I didn't have a Conan release CMake presets because that's not in the other project, so I just need to basically just do some copy and pasting here. And whenever I have the Clang stuff, I can also say colon release, right? Good. So this should be still working. Could not find toolchain file release colon. Yeah, that's quite correct because we're not building for debug, are we? If we select preset and we do a Ninja Clang debug. There you go. All is fine now, and we can finally include FMT, right? If we do the right thing here and come down here and say target link libraries. And we have emulator, private, FMT. Right, that should be Gucci now. And we should be able to come here and say FMT and format. There you go. Good. Why did I do all of that? Just because I want to say something like, well, also we have the print library. Oh, we don't have print available to us. No, so the Clang doesn't yet support print. So for those who don't know, print is the new stdio library that allows you to do print line and whatever in C++. Print header. I want to see why it's not. But it says C++ 23 here. The library is print. But does it not support on Clang? So Clang compiler. So if you look at the compiler support, we have the print header, formatted output. So we do, yeah, I mean, it seems to be supported by Clang, right? So 17 partial. Oh no, Clang 17 doesn't actually support it. Partially support it. I don't know what that means, but that's kind of annoying. So we can't use it, yeah. That's fine. Let's move back to IO stream then. So stud, cout, fmt.format. Oh, right. So we have command and then the operand here. And does FMT support? Does this support hexadecimal values? So FMT C++ hex values. Of course, the only thing that you want to use is the partially implemented one. Yeah, of course. It's very annoying, but so hexadecimals, hex. Right, so how do we do the hash option causes the alternate form to be used, okay. Wait. Oh my god, this is gonna be quite a read. Hex format, right, so maybe this? Does this work? Why is CL not being recognized? Do a clean rebuild here. Things seem to work, operand and clean rebuild. Return of a non-void, that's fine. Okay, that's good. Of course, we want to basically just pass in the CPU here too, I guess, right? So CPU const Now this is going to be very inefficient because we're going to be creating a new memory every time, which is 65,000 bytes. But I'm happy to just let it run for now, just to make it as simple as possible, so I can prove my point here that this is basically a state machine. Okay, so once we have that, I mean, there are, obviously you can see how we then implement other stuff. So we can have another one here, which is going to be whatever in the hex dump we have. So 85 is the next one. And this here, by the way, is the LDA with the immediate value. So something like that. The recreation of the CPU for every instruction performance. Yeah. You know, that kind of performance issues that we're talking about here. But it's fine. For demonstration, it's okay. Obviously, we can change this in a second because we can just modify the actual CPU, right? So for example, like, we don't really need to return anything here. We can just call it void. And instead of const, we just pass a reference to it. And yeah, we can just modify the CPU here. Not a problem at all. I'm going to create some functions to actually help us now. So yeah, this one here would be, I don't know which one this is. So store from the accumulator to the memory address. Right, so what was this again? Yeah, this is 0 page. So store into the accumulator from like XX. It's the memory address XX. That's what it is. Now I got to think about how I'm going to read this, because basically we're going to have to read by. And we're going to have to do jumps based on the number, based on this thing here. Huh. Maybe this function is actually not the right one. Maybe we have to just, you know, execute next command or something, right? And instead of taking the command and the operand itself, we just take in the, like, a vector of bytes, right? Which is actually the whole program. Yeah, so the program here, and wherever we are now, so std size t. This is the reading position here. So in here, yeah, we want to kind of like read 1 byte for the operand, and then read either 2 or 3 bytes for the operator. And here is the operand, right? I'm not sure if I'm using this word correctly. Is operand what I think it does? It means what I think it does. Operand is the term used in computing, programming, and mathematics to refer to a value or expression that has been used to perform an operation. The operand indicates what item to apply the action to. I think it kind of works, but yeah, let's see. Yeah, so let's see. So we want to do something like, you know, if the position is kind of more, I guess, or more than or equals to the program.size, we kind of want to return an error, right? So I guess in this case we do return an error, like a boo or something. And of course this is not Rust, so we need to put this in there. What's the issue here though? Okay. Right, what's the issue here? Oh yeah, vector is not a thing. Let's make these things a little bit nicer. So that goes there, this goes here, okay. All good. All Gucci. And now we're gonna have to get the command itself. So very easy in this case. Auto const command. It's gonna be the program at wherever this is. So at the position. And then once we know the command, right? So this is where this comes in. We're gonna read however many operands we need. How many values we need, right? So either this is like 1 or 2 bytes. This is always either 1 or 2 bytes, right? But in the case of A9, it's just 1 that we need, right? So we kind of need to do something like auto const value is going to be equals to, I guess, the program. And now this is the interesting thing, because we also have to do a check here. So we need to do if the position plus 2 or plus 1 actually is bigger than or equals to program dot size. We're going to do the same thing. Oh, what am I doing? It should be more than or equals to. And if not, only now that we can read the program basically. So program.at position plus 1. Right? Position plus 1? No, this is not quite right. If the position... Yeah, no, that's correct. Yeah. Position starts at 0, so it's more than or equals to. That's good. That's good. So why is command not working? Cannot jump from switch statement to this label. Cannot jump from switch statement to this label. Ah, stupid. You can't skip initialization in C++, right? So I like how he gave me the exact error that I needed, right? And not just some random error. So, okay. Yeah, I think this should be okay for now. And then obviously we need to do, you know, LDA immediate. This is what we're going to do here for every kind of function that we need. So let's define that. So void LDA immediate. And we have the CPU in here, CPU, and we have the value stud uint8t val. And all we got to do in this case here is just do the register.a is going to be equals to val. That's it. That's all we do. All we do, because it doesn't set any flags or anything like that, and we can check that by actually looking at the documentation for it. So for example, this one here, you have this particular one that we're implementing, so the LDA immediate mode. So it takes 2 cycles, and okay, good, yeah. I mean, we're fine with that, right? Good. And it doesn't set any flags or anything like that. Yeah, it doesn't set any flags. Oh, it might do. It sets those 2 flags, so the 0. Okay, so now we have to read it, I guess. It sets the overflow a negative. Oh. How does that work? So 6502, that's not giving me a very good documentation. So because we might have to set some flags. Here's my ignorance, trying to work out what the code does and struggling a bit. Am I right thinking the 0 flag gets set to 1 only if the value loaded is 0? And it's cleared if the loaded value is non-zero. Loaded includes popping from the stack. Okay, so basically we set those flags, right? So we kind of do need to do a bit more than this. So if, for example, val is 0, then we want to say that the CPU.flags. Ooh, how can I get the first one? Does that work? Does it work like this? Yeah, so this is the 7th one, right? That's the 7th. Is 0. Oh no, it gets set if it's 0. An overflow. How does it overflow? How can you set something, an 8-byte thing that overflows for an 8-byte integer? I'm interested now, because I have no idea. That's what this is saying, right? Yeah, so it sets the 0. Oh, it sets the 0 flag. My bad. The Z flag. What is the Z flag? Yeah, I mean, that is the overflow flag, isn't it? Oh. Wait, what? I'm confused. This is... One, two, three, four, five, six. Oh, okay, so I'm just reading this wrong. I'm reading this wrong because this is in the opposite order as what this is. This has C and N. And this has C and N here. Okay, that is interesting. But anyway, which one do we set here? Let's go with this method, because I'm going to be looking at this page anyway, so... So 1, 2, 3, 4, 5, 6, and then there's another 2 bits that I have no idea where they go. In between what? I'm just so confused now. So it says the N and the Z. N is negative. How can it be negative when you push something in? I'm still confused. After most instructions that have a value result, this flag will either be set or cleared based on whether the value is equals to 0. We know that. But what about the negative? After most instructions that have a value result, this flag will contain bit 7 of that result. Ah, okay, so is it like, it's just checking for a 2's complement, I believe. So bit 7 of that result. Yeah, if bit 7 is 1, then okay. That's fine. I mean, we can do that as well, right? Let's do that. Let's see if it's right. So essentially in here, we have to check that the value is 0. And if so, we're gonna... Let's undo this, because I've no idea what even that is. So we want to set negative to the most kind of... So the biggest bit. And then we want to set 0. So the Z flag. Okay, so this is 0, 1. That's the 6th. Yeah, this is the flag 0, and then we have another one here as well. So if the value... I guess we can do a bit shift, right? A bit. Sorry, not a bit shift, but a mask here. 0 by 0, 1. There you go. So if we mask it with this, then it should be set. We should set a negative flag to 1 as well, right? I believe. In fact, this is even simpler. This is even simpler because this is just setting that anyway, right? So CPU dot flags 0 equals that. Right? I believe it is anyway. Yeah, this is the same thing because this has to be reset as well, I think. So basically what we're doing is checking that the val is 0. And that's it. And I think that's it. That's all that we need for the LDA immediate. And then we pass in the CPU here and the value. Right. That's good. Now, let's do the other one. The only other thing on our little emulator here, which is 8.5. 8.5 was store whatever we have on the accumulator to the memory address, right, that we get given. Let me just look at here anyway. So we have LDA, we have SDA. That's what we're going to be doing. So again, looking at the CPU instructions, we have this particular mode here, store accumulator into memory. What we do have is the 0 page, I believe. No, not even that, right? Is it 0 page? It's one of these two. Yeah, so it's whatever is in the 0 page. Is this one here. So it takes 3 cycles. I'm going to put these things in here actually, so we're aware of how much time this should take in the end. So this should take 2 cycles. Yeah. And this again should take a few cycles as well. Let's put that in now. Three cycles, right, that we read. Yeah. And kind of the same logic here. I'm just going to copy and paste. Obviously, we want to kind of refactor this a little bit and not do the same thing over and over again. But for now, it's fine. Oh, sorry. So we have a value, and what we got to do is basically call STA immediate node here. Or 0 page, STA 0 page. And we have the CPU and the value. And we can break, right? And in here we're gonna just return true if we run everything. I do wonder if instead of a Boolean value, we should return the actual number of bytes that we read. So we can then use that information on the function that's obviously going to be calling this, that's going to read into everything in the program. But yeah, let's do that. I think that's a good idea. So a return value of 0 kind of means that we didn't really do anything, right? So a no op or a So we read 2 bytes overall here, and the same thing here. This is obviously very inefficient to anything that you may find online, but it's just me learning how to do this. So void LDA, so sorry, SDA 0 page, and we had the CPU being passed in as a reference here, and then the value, which is a uint AT. Ooh, Can't spell value today. Yeah, so what do we do here? Now it's very easy. So what we do here is like we take in the memory at the particular value, right? That's what we want to do. And then we kind of want to store whatever we have here. Yeah, we guarantee that this is going to work as well because it's a uint8, so it can't go off bounds anyway. Because it's definitely between 0 and 255. So there's no error handling at the moment. And that's going to be simply the value of whatever's in A, right? And that's it. Now, which flags does this set? This sets none of them. It sets absolutely none of them, which is good. That's what it means, right? When it says this. Anyway, I'm gonna take that as a no, yeah. So it can set these flags. This operation can set these flags, and when it doesn't have anything, it can't. So this is basically it. But yeah, I mean, we somehow have a little function that handles these two things. Now we have just one more, I think, which is the 00, which is break. So break is kind of a special case. Oh yeah, by the way, this can be 1 as well. I forgot about that. Some instructions only have the instruction name and nothing else, like this one that we're going to see right here. So let's add it to the top. Why is this like... There you go. So 00 is break, and 00 means finish the program. And yeah, that's what we have. So 00 break just means end. And we're gonna look at bytes read, I guess. 0. Now, I've just realized something. There's no way to differentiate between 0 return from a break and an actual value of 0. Sorry, an actual error of 0, right? So in essence, we're probably going to change this to an optional here, because we don't have the result type that Rust has. Otherwise, it will be a result. And we can... So we have optional up here. And that's going to go in here. Now in here we're going to return a std no opt. In this case, this remains 0. This is going to be a std no opt in here. And this is also going to be a std no opt right there. And then a std no opt. So this is like an unsupported command right there. Yeah, I wonder if we should run this now, right? So we obviously have a function that executes the next command, and that's not an exported function. Now we do need an exported function that's actually going to run all of this, right? So export. Let's look at export, execute. Just execute all of them. And in here we're going to take the CPU and then the whole vector of the program. And this is going to, go and execute all of them now. So what we're essentially going to do is like we're going to do an auto, actually a std size t position is going to start at 0. That's what we're going to start on the program, right? I do believe that the program in an NES game doesn't actually get stored at 0, but for the sake of this emulator, we're going to start, you know, program assumed to start our memory is 0, right? Then we're going to do while, I guess, position is less than the program.size, right? Yeah, I mean, this comment doesn't even make sense anyway, because we're loading it from a vector. Export, and we want to do yeah, while we have some stuff, so we have CPU, and we have the program here, and we have the position. No operator plus matches the operands, types of size t, and optional size t. Okay, yeah. So I guess we do gotta do a maybe increment. That will be something like execute next CPU program and position. And if it somehow did not work, there's something wrong with the program, right? So we gotta kind of return it now. So return false here from the function. Otherwise, we can safely dereference it here. And we go on to the next one. Yeah, so let's try this now. So basically, I do want to read the binary into a file now. So I guess the emulator part is kind of done. Let's add an app here. So a new folder, emulator app. Let's do a new CMake lists. I'm just going to copy and paste that now. Adding FMT as well for printing, pretty printing. I think that's everything that we need for now. Let's do another file. Now, what's the best way to read a binary file in C++? C++ read. How to read a binary file to a vector of unsigned characters. There you go. So I think iStream is good. Yeah, iStream both iterated. That seems like a good one here. Can we cast all of this stuff? Reading from binary file to a vector of uint8. I guess we can just safely cast it, right? With the iStream both iterator. so all these all these examples are so complicated. There you go, that's the one I kind of wanted. It doesn't have to be that efficient, right? Let's get that example, string buffer iterator. This is kind of what we want. What do I need to actually be able to use a module in here though? I feel like I'm missing some CMake stuff to actually include the module library. So for example, in my tests, I had that. Yeah, nothing too special from the looks of it, just import at the top. Seems to work fine, right? So basically we can do an import. Emulator, hopefully. Now, emulator itself didn't compile. Why? Use of undeclared identifier execute next. What do you mean? Ah, yeah. My bad. My bad. My bad. Let's put it all at the top, I guess. Okay. There is one thing that didn't work. LDA immediately use of undeclared identified. Undeclared identifier. Yeah, that's fine. We can just put it all at the top again. Kind of annoying though that in C++ you have to define the functions before they're used and it doesn't know about the ones on the same file. Let's build it again. Better. And here we want to return, I guess, bytes read. Expression result unused. It's not unused though, is it? It's not unused. Non-void function must return something. Execute. Okay, so if you got to the end, we can return true, I guess, right? How is this unused? I don't understand how this is being unused in here. Ah, yeah. There's no return. Oh, I've been writing too much Rust, guys. As you can probably tell here. Too much Rust. Ooh. Okay, that's better. Now, going back to the emulator app. We can include that here. And then we can do all the include vector stuff here. Just load it as character, I guess. And the file itself, auto. Okay, so now it's gonna do some basic checking here. So if arg c, I guess it's less than 2. Just want to print out the errors here, guys. Nothing interesting. This shouldn't even need FNT. Need to pass. And then we can return. So return -1 or something. Input file stream. Let me just do that. Okay, so by the end of it, vector of car should be our stuff here, right? And I'm kind of guessing that we can save this to a... Let's do some modifications here. Ooh. Okay. I'm guessing that right now we can kind of just call the emulator itself. So do like emulator or execute or something. Execute. Yeah, let me add this to the program in the first place, right? Oh gosh, this is getting a little bit difficult. I mean, the difficult bit is doing everything around it and not the actual emulator itself, as you can probably see. Right, Robin, you're still here, dude. I'm impressed. You have some patience, man. You have very good patience. Yeah, so we just need to add another emulator app here. And then we can do a build, hopefully. Okay, but now in the emulator. Hello, Slim. How's it going? I truly don't. I think you do, man. You have more than me anyway. Undeclared identifier. Execute next. Is it just execute? No matching function, so emulator. Dude, like, why is IntelliSense not working at all for my emulator? What am I missing? Let's take a look at my other one. Came back from late prayer, so I'm late, bro. No worries, man. I mean, do what you gotta do, innit? Are you fast? Is it fasting season now, Slim? I think it is, right? I'm not sure, actually. I remember seeing it on the news. Yeah, okay, it's Ramadan. Right, nice. So, right, what the hell can we do here? So we're using export module C++ pp. And then how do we use it? So it's just base64 pp. And encode begin. Actual encode, whatever. Does it not get namespaced? This is kind of shit, isn't it? Yeah, Redemption, hope you had a great first fasting day, Slim. Yeah, yeah, me too, man. Because it's difficult, isn't it? I'm starving the whole day already. Like, I can't imagine what you guys have to stop yourselves from eating. Because like the whole day, it's just I wouldn't be able to do it, man. A lot of like willpower. And props to you. I had this IntelliSense error when I worked with modules, never fixed it. Yeah, so I think IntelliSense is just not working with modules right now. Whatever the LSP is, they clearly haven't implemented modules yet. Yeah, it's hard, but it's cool. Get rid of toxic. Yeah, that's true, yeah. Eating is not a problem. Water is tougher, yeah. Well, you guys also don't drink water for like the whole day? That's crazy. I just program and forget to eat easy. Yeah. I did that sometimes as well, man. So it seems like we're not going to be able to... We need a CPU, right? So we need a 65, easy 65K. Does that work at least? I mean, the CPU bit did compile. Yeah, and that actually takes me to the right place. Now, the thing I don't like with modules is like it doesn't automatically CPP namespace them. Yeah, no eating, no drinking, no bad thoughts, no misbehaving, cursing at others, etc. That's crazy, man. Yeah, props to you guys. I hope you're doing well though in these times. So how long is it for, out of interest? Is it like it's like it's over a month, right? Or am I just talking shit here? It's a long time. $30 days. Oh, it's exactly a month, right? Just the C++, you forget about it. It's 30 days. Alright, yeah. Yeah, man. I bet at the end of the 30 days, though, you're gonna eat like so much all the time. Is that like, do you lose your hunger after a while? Because like, if you do the same thing every day for 30 days, you probably get used to it, right? So is it difficult having to get used to like eating multiple times a day again? Sorry for the questions, by the way. I'm just interested. You feel weird after 30 days and not eating in a day. The first 2 days is hard. Yeah, I can imagine, man. Export namespace. Okay, so I have to export the namespace. All right, so if I do, I'll go back to this one here and emulator.cpp. I do export namespace. Okay, so my export is working now. This month is easy because we break fast at 6. 3 years ago we broke fast at 9:30. Why does it change? I thought it would be like the same every year. Yeah, 9:30 though. Like not eating anything for the whole day until 9:30. It's crazy. Like. When the sun goes down. Ah, okay, I see. So it's to do with the sun. That's interesting to know. I remember when I was at school and I used to play football, like five-a-side with some of my friends. I think a couple of them are Muslim, so I remember like we used to go in the afternoon and they would play for like 2 hours without eating anything the whole day, and they still have to wait until later on at night to eat stuff. That's a lot of willpower, man. It's going for the lunar calendar, which is offset by 10 days. So every year is 10 days earlier. This way Ramadan can fall on any month of the year. Ah, I see. We'll do it for the poor people and better or so. Yeah. That's, yeah. That's a good, that's a good mindset, yeah. I mean, in the summer it's insanely hard the further north you are. In Germany, for instance, a couple of years ago, it was 18.5 hours without eating and drinking. Yeah, dude, that's crazy. Yeah, props to you guys. Like, I'm gonna try not to drink that much out of respect now, so I'll leave the drinks aside for the rest of the stream. Right, so what am I missing here? I've got the export namespace emulator, which is working. Or is it? Is it working? Right, this bit is definitely not working. It's fine now. We are drinking as well right now. Ah, okay. So you're not in random. Oh yeah, of course. It finishes at 6, right? There you go, I was actually getting quite thirsty. Yeah, so I guess you guys have it very easy this year. At 6 you can just like eat as much as you can. So do you eat like whatever you'd eat in a day in one meal? Is that what you guys do? So like you're not as hungry the next day, I guess. Because that makes more sense, right? If you can eat as much as you need. You just eat more, which is like once a day. Right, what the hell? Why is it not working here? Followed by must be a class or export declaration appears within another export declaration. Ah, okay, right. So these things can't happen. So you can't have, if you export the namespace, you export the whole thing. So these will kind of go there. And then these things can go outside the export as like an inline function. Incomplete type is not allowed. What? But I kind of need that. I kind of need that type. We eat nutritious food like oats. Alright. That lasts a long time. Some do, others don't. I can't eat as much after not eating the entire day. Yeah, I can imagine. Yeah, you'd essentially get used to it, right? Which is, I guess, good in the sense, but bad in the sense that you can't eat as much. So. Right, so I guess what we're gonna do is like, oh, we have a problem though. I need those struct definitions a little bit before. That's fine though, I can just put them separately. Up here as well. Oh, very annoying, but not sure how I feel about working with modules in C++ yet, to be honest. Yeah, emulator. I don't even know what I'm doing anymore. Right, and then this one also needs an emulator. There. And it's Gucci now. And we can remove these other definitions that we don't need anymore down here. So I cannot find link FMT. Yeah, that's probably because I didn't do it right. There you go. Wait. We need to find package FMT required here. What is the issue? FMT, FMR? What? FMT. Okay. Right now everything's built, so I mean, it's built, but IntelliSense thinks that there's a mistake here, but that's fine. Execute, and then we need the program. Yeah, I guess we can convert everything now. Ooh. Not gonna lie, I love VC package, Conan, so I don't know, it's like first love. Yeah, maybe it is. I mean, my first love is Conan, so like I'm more used to it, and I can kind of work out the problems a lot more easy than in VC package, because I know the model fairly well. Like I've read the source code multiple times, I hung around in their GitHub sometimes, so for me, it's a little bit easier to debug. But both of them are good for any project. So yeah. Now the thing is, we've got a vector of character here. So what we do want is we want to convert this to a, I guess what we do want to do is like a vector of program car. We want to do uint at here, the program itself, and then we have I guess we can reinterpret cast in this case. So I think this works. I'm trying to work on a project that uses local imports, no Conan or likewise. I'm trying to configure the build of CMake, but I'm struggling a bit. Do you help others with projects if you have spare time? Yeah, of course, Robin. So if you're trying to include things with CMake, not from like a package manager, I mean, there is a next best solution. If you're on Linux, there is something called package config, which works fairly well with CMake. Failing that, you can, I would recommend taking a look at writing the find files. So find package CMake. So if you look at how you can write your own find file, I'm sure that you might have some more luck with it. So basically, you just got to find the library files, the header files and stuff like that, and you're essentially just writing a CMake script to do that automatically, which by the way is what Conan and VC Package do. They just wrap around the defined files quite well. So yeah, have a look at that, and if you're struggling, push it up to a GitHub project and send it my way. And whenever I've got time, which will be most likely on the weekend, I can maybe sit down with you and then we can screen share or something. Righty, so yeah, CST left, let's build it. Okay, what's the issue here? No matching constructor for this. I do wonder if instead of doing the program, I can kind of just pass in an std size t here. Very lazy, I know, but actually, not even that. Let's pass in a spam, shall we? Will do. Don't have much time today, so I can look at it tomorrow. Yeah, no worries. I mean, take your time. Can we do a spam here? Which is just a fat pointer. Yeah, I think we can use a spam instead. Let's remove the vectors from everywhere, shall we? This is C++23 after all. So we've got a program here. We don't need a reference anymore, but we do need to have it as a spam. Spam, for those who don't know, is essentially just a fat pointer and things. So get app position. So what can we do here? So we have that operator. So we can do operator position, right? That still works. So command is equals to that. And then in here we also have the operator. Any other problems? Any here? Okay, why did I turn this into a spam? Well, I turned this into a spam because now we can simply do a reinterpret cast and call that. I know it's very, very lazy, I know, but easy 65k is what we need here. A program and then we can do a spam, which I believe would be some sort of like reinterpret cast down to stud uint 8 t star here from the data of the program, and then the size of it, so program content dot size. I think that should be okay. All right, yeah, there you go. Yeah, I mean, we can kind of debug this now and see if it works, right? That's what we want to do today. So hopefully this is the entire program that I wanted to compile here. I wanted to basically compile a very easy emulator that just supports a couple of instructions and can run a test program that we've compiled online already. And the test program itself is this one here. So hex dump. Oh, not this one. This is the program itself. It's a very, very short program. It just loads something into the accumulator and then stores it in the memory somewhere. So yeah, let's create a debug.json file, shall we? So C++ debug.json, and we're going to add a new configuration, and we're going to simply do a gdb launch. All right, and then the program itself, I kind of need to see what the program is now. So build emulator app, right? Emulator app, yeah. So we've got build here, and then we've got Unix deb ninja emulator app, or emulator app. And the current work directory is simply going to be workspace folder. And I think the rest is fine, right? We just want to start that emulator app. Now let's see how it goes. It didn't work. Why did it not work? It didn't work because we need some actual arguments, right? That's what we wanted to do. And the first argument should just be the file name. So the file name is going to be whatever this file is here. And if we just do it again, we should get further now. There you go. Right. Ooh, okay. There you go. So we're executing the program now. We're at position 0. We can see that the program is 251. Ooh, can I change this? So 169. What is 169? Is that A9? A9. So if we do... Yeah, A9. Sounds good. Sounds like it worked fine. So... I just wish that this was showing me this stuff in hexadecimal instead of... Yeah, maybe we can change that. Can we change this to show it as a hexadecimal instead? So VS Code, C++, GDB, show bytes as hex. LLDB display format, right? Oh, hexadecimal. There you go. Beautiful. Let's run it again. That was too easy. It felt almost too easy. A bunch of C++ stuff now. Now position is there. Program. Yeah, it's still not hexadecimal. I don't know. But anyway, we can kind of go into execute next. The command is A9, and it should be down here. And we do get a value. We have a value of 1, and we load into the accumulator, right? So what we expect to see now is the registry flags A equals to 1. That's what it sets here. And the flags are kind of, well, you can't see them here because they're bit sets, which is a little bit weird. I wish we could see them here. We can't actually see the memory. Oh no, we can see the memory. We can see the memory. But yeah, And then the next one, we're going to have to say that we've read 2 bytes, and bytes read. And then we increment the position by 2 in this case. And the position here is 2, and the program size is, well, 4 in this case, as you can see here. So we're going to go into the next execute the next instruction, which was to store the memory at the CPU, right? Store whatever it is, a value. I can't remember which value it is now, but we can see it here. So B1, what is B1 in this case, right? We can kind of see. So let's go into this, put B1 here. 177, that's the value. So we expect the 177 index to be equals to 1 now, because that's the value that was at the registry flag A here, right? Or the accumulator. Ooh, that's going to be interesting though to see. 177, there you go. Seemed to work, right? So that seems to work fine. And what's cool about this is that we can actually, like, once we've done something like this, we can go on and implement some tests. So we can basically just write some unit tests on this stuff, right? So let's copy and paste some of this. So there you go. So include ctest here, add test. It works nice, yeah, it does. It reads this, it should read this binary. That's what I mean, like it should read this binary because we support all of the instructions used in this binary. What we have to do now is to expand things, right? Is to accept more instructions from the instruction set until we cover all of them. That's what an emulator is. But let's add some tests here so we can see if some of the flags have been set, and you know what I mean, right? Let's create a new folder, so call it tests, and in here I'm just gonna put that CMake list in there. I'm gonna include that ctest in here. So base64, no, we're gonna call it emulator tests, and emulator test.cpp, emulator tests, and we're gonna link into the emulator and gtest. This is going to add the emulator tests to my ctest executable, so whenever I run ctests, this is going to run. And I can add a new file here, so let's call it, well, it has to be called emulator tests.cpp, because that's what we've done already. Let me add also, just tests, right? Gonna add that there. You can see gtest was found because we already have that with Conan. We added it earlier. And now, I'm just gonna copy and paste some of the boilerplate code. I cannot be bothered doing it, so. This is what's gonna go in here. We're of course gonna do an import on emulator up there. And I'm just going to copy one of the functions here so we can, I don't have to make any typos. There you go. So this is emulator, 64 emulator tests. So emulate LDA immediate. That's the function that we're going to try now, basically, right? So it becomes very easy in this case. I mean, we have the emulator there. So what we want to do is, like, we want to create a CPU. This test might use a lot of memory. Yeah, that'll be fine though. But we're going to create an emulator.cpu called, was it CPU like this? I can't remember now. Yeah. And then what we're gonna do is like call emulator.emulate or execute, right? I believe it is. We have the CPU being given to us and then the program here. Now it becomes easy now because all we have to do is like create a span. Or a vector really, a vector. Or yeah, a vector. Or even an array in this case, yeah. This is not going to change, right, in the test, so it doesn't have to be a vector. I'm going to leave that as 10 for now, but we're going to find out what it is. And then the program data here. And this becomes very easy because we have A9 here, right? That's what we wanted to test. And then the next one is something like, what is it? Let's move the value 10, right? What's 10? 10 is A0, right? A0, 0, 1, 2, 3. Oh no, it's 0A. My bad. There you go. So this is the simplest program that we can emulate, and the size is 2. And I think program already gets converted to a span because there is that implicit conversion from the stud library. So I am forgetting to include gtest here. Gtest.h, I think it is. There you go. And this should all compile, right? So let's build everything and see if it actually all works. Emulator is not found in this scope. Yes, it's not. Why is it not? Why is it not found in this scope? Do I need that in it? Oh yeah, I do. I need a semicolon. Which is fine. I mean, I can obviously debug this test now as well. So if I create another one, so let's create another configuration, which will be, I'm just gonna copy and paste this actually, guys. I can't be bothered. Today's copy and paste galore. We don't have arguments in this case. And yeah, let's see if we can run that now. There you go. We've got the program and we have execute. So running command A0 of A, and at the end of it we should have, you know, the expected values to have A with 10, which is, it is what it is. So what we can do is like, we can do an assert, I believe it is, assert equals down here that the CPU.register.a is equals to this, right? And all the flags are still the same, right? So we expect, we should probably assert that everything is what we expect. So we have X is going to be 0, Y, stack pointer and whatnot. These is going to have to change as well because, you know, the program counter should be updated. That's something we didn't do. We didn't do the program counter update. So yeah. Maybe that's what we can do now. I've got another 15 minutes or so. X, Y. We've got the... What is it? X, Y, SP, and PC are all down. So this value here for the program counter should have been updated in the emulator when you think about it, because that's what actually keeps track of the position of of the program in the CPU, right? So in essence, we don't really need to send this position here. We don't need to, because the CPU already has that, you know, right? So what am I trying to say? I'm trying to say that whenever we calculate this position here, yeah, so whenever we do position, we should be doing CPU.flags.pc in this case. Oh, not flags, so register.pc. So CPU.reg.pc. because that's what the program counter is for, right? When you think about it. So we can completely remove this and let the errors pour in. cpu.reg.pc +1. Okay, and at the very end here, we don't want this position anymore. So what we do want to do here is, as you can probably guess, we do cpu.reg.pc is equals to that, right? And then again here, while the cpu.reg.pc is less than the program size, we keep going. So that's one of the things that we've been able to tell from the tests straight away, a good thing. And now you can probably tell that we don't expect this to be 0, 0 anymore. We expect this to be at 0, 2, right? So it's going to be past the array. So that's what we expect in the end. Usually, you know, this kind of... Do I have a test? Yeah, let's run a test here. No tests were found. Like, what? Can I find all the tests somehow? Debug tests. Refresh tests. Is it because I forgot to enable testing? So... This song is kind of crap. Enable testing in CMake. Yeah, that's the one. I forgot to enable testing in the CMake. Let's reconfigure it all. Let's refresh all the tests. Matt, I'm preparing a PR for Urchin, adding some documentation for it. Oh, nice, dude. And easing up the development process by providing an easy-to-use development setup. Probably will finish it next week, though. Oh, thank you very much, Dear Redemption. By the way, you might want to check out the Docker Compose stuff if you want to add to that. That's supposed to be the sort of like easy development for it. So if you have like Docker, it's just spin it up and then you should be able to develop from there. But yeah, I'm excited to see your PR, dude. As soon as I get time, I will look at it, and it'll, you know, as I said, it'll most likely be on weekends if I'm like doing videos on the day, on the week, and working during the day. But you know, there's no rush, man. You know, take your time. Helping is already good enough. So. The non-zero flag. let's look at the documentation actually and then work it from there, shall we? So LDA is what we're looking at. And if you go to the very top here, we have the absolute, and immediate one is what we implemented. And that can set the 0 flag and the, what's the N flag again? What is the N and Z? Negative flag. The flag will contain 7-bit. Okay, yeah. That's cool. This is just for like, I guess, so we can calculate with if it's a negative or not. So how did we do the flags? Because we got to figure out, oh, we don't need this anymore. So we want the N flag to be set to 0. Well, in this case, it's going to be 1 anyway. But we do want to check the 0 flag, which is the second to last one, right? Second to last one. So second to last one, right? I'm confused now. Yeah, second to last one. So we expect this one to be 1 here, if it's 0. And likewise, we have negative values now. Negative in the sense of, I think this is a 2's complement, by the way, I'm not sure. I need to read into it on how the 6502 represents negative offsets. I think it's 2's complement, if you guys are interested in figuring out. Well, I gotta go have a nice rest. Thank you, Robin. Thank you for joining, dude. And I'll catch you some other time. We're nearly done with the stream anyway. Right, so negative, that would be something like FF, right? Or F. 0 to FF. Yeah, 0 to FF. And what we do expect now is the 0 flag to not be set. Let's build it. And going back to the tests, we have, let's refresh all of them. And one of them did fail. Ooh. Which one is it that failed? Cannot merge previous GTS profiling. Emulate with negative. Okay, so this is not working fine. Let's put a breakpoint there and debug it. So that one passes, we know that. The negative one does not pass. Ah, yes, it's because it's A9. And what we want to do... Oh no, yeah, LDA is still the right one. Let's run it again. These songs are making me fall asleep, man. So 255 here. LDA immediate. So we have 8 equals to 255. Flag 6 though. So flag 6, which one is that? So val is equals to 0. Yeah, this should be true. This should be true, right? So right. Now if we look at CPU and flags, 0 is equals to 1. What? Wait, how do I even... Maybe I'm not working with the bit sets very well. string bit set. How can I compare one value of it? Access operator, bitwise and, bitwise or. Accessing bit value at index 1 of bit offset 1. So bit set. That should have been 0, right? Yeah, no, this works in the way that I expect it to. Okay, I think I've flipped it a little bit. So index 1 is kind of this one here, right? Oh, maybe not. Wait, this one works. So why is this one not working? I mean, the code that's kind of setting the carry flag works, but the code that sets the end flag does not. And that is confusing to me. That's very confusing to me. That is very confusing to me. I think I'm accessing it in the wrong way, maybe? No, it can't be. It can't be. So 0 is the least significant bit, is that correct? Is that correct? Initializing the first n positions to the corresponding value. Okay. There is no notion of ending this as far as the standard is concerned. When it comes to bit set, defines bit position. When converting between an object class bit set n and a value of some integral type, bit position n pos corresponds to the value 1 over n pos, the integral value corresponding. Okay. Initializing the first n bit positions, the corresponding values. Okay, a val with binary representation 1L leads to bit set of n, b with bit 0, n, bit 1. Wait, what? 11. Bit 0 and 1, and remaining bit sets are 0. Okay. So it is kind of wrong, I guess, right? The way I should be using this is instead I mean, the carry flag is there, the Z flag is there, the I and D is there, and then the B1 VN. This is how I'm using it, according to that then. Which means no, that was correct. That was correct. Never mind. Yeah, because the very first one should have been C. Oh, no. That was not correct. I was right in this one. The CZ ID here and B1 VN. And then we can continue as it is. Yeah. Let's build this and then try and run the emulator again. .255 and this should be equals to what? Okay, so flag 0 wait a second, so 2 tests failed, or it should have anyway. Where is the 0? Where in the hell is the 0 flag? So there's in 2 here. 3, 4, 5, 6, 7. Okay, yeah. Gosh, I am using the wrong one, that's why. All this time to figure out that I'm using like the wrong freaking thing. Right? Or no? No, this is right. I don't understand. Don't understand. Let's see something. I'm gonna print every single one of these. I am gonna find out what values they are, one way or another. Right. Okay, so that kind of fails before it even gets there. What? Let's try that again. So, register A is 255. Okay, yeah, so that... Oh gosh. That should have been FF here. All this time to figure out that I've made a typo. This feels so good. Feels so good right now. Let's try it again. I hate when that happens. Yay. Okay, something else failed though, with 0. So CPU registry, we're fine. So flags 1 is equals to 1. What the hell? See, expected quality of these values. which is that, and this, which is 128. Does it just not support equality, I guess? So 2 tests failed. We went from 1 test to 2 tests failing now. It's not as good. Oh gosh, this is not good. And we've got a leak as well, on top of everything. Guys, I'm going to call the stream here. I need to figure out what's going on with the flags, but I think most of it is kind of working, except the flags that we're setting isn't quite right. I believe that's probably because I made an error somewhere. What's with the test that's working? That's just working. The issue comes when we read an instruction that's supposed to set the flags, and I'm pretty sure I'm just not using the bit set type correctly here, because ideally, like, whenever we set a 0 to the registry A, then this flag here is supposed to be set, so the second flag, or 0, 1, right? And is that what we do? Let me check. If it's 0, flag, oh yeah, so flag 1 is supposed to be set. If not, flag 7 is supposed to be set. Maybe that's the mistake I've made. But let's see, let's see. We do have a leak as well somewhere, which is concerning, but I will find out. Usually that's just kind of, sometimes that's a false positive. Okay, that worked, and this worked as well. But we still have a leak though. We fixed one bug, but I have no idea what the leak is. Does not work on the p-trace. Maybe we can do the verbosity here. Yeah, I mean, it would be nice if we could see where, which leaks are we going over. But you know, test kind of work now. We have a leak. I need to figure out where that is. But calling the stream here, guys. I'm kind of tired and I need to wake up tomorrow morning. But it's been good chatting to some of you, and thank you all for joining. I will kind of go now, so have a good night and I'll see you next time. Bye bye.